Good morning, my dear friends. Okay, so now we shall continue with the problem. Okay, sir. Now, but now in the problem, what he has asked is determine the maximum principal tension. He has asked. Okay, now the question is okay in this given problem where I should calculate the maximum principal tension. Okay, where I should calculate the maximum principal tension, whether it is here, where. So for that your IS code gives you few this thing. That is what I have said. It is there in the note. Okay, notes whatever I have given 1 2 3 4 5. Okay, it is there. So what the code says is now, Baba, consider the element at the lower junction but in the web. Okay, in the sense, see now already some load is now acting on this beam. Am I right now? So now the beam is going to now bend like this, as you know. Okay, so since it is in the working condition, I have to consider one element at the lower junction of the flange and the web, at the lower portion. In the sense, here I have shown, see now, here is the element. Okay, here is the element that I am going to now consider. But this element is in the web only, not in the flange. It is at the junction, but it is in the web. Understood or not now? So now the first element I have to consider it as now here. Similarly, your next, in sense now your AS code also says you have to examine the element at the CGC. Baba, you already calculated where the CGC acts. Okay, so it acts at a distance of 250 mm y bar. Okay, so you will have to consider one element at the CGC also. So now at this point and at this point you will have to calculate the maximum principal tension. So now in the beginning I will consider the element here now. Okay, see now, that's what I have said. Consider an element at the lower junction but in the web. Okay, now you know that the shear stress on the element is given by tau v is equal to Vc Ay bar divided by Ib. Am I right, sir? No, this is the equation which you have seen in your shear chapter in the beginning. Vay bar divided by Ib. Okay, sir. Now, so now we will try to calculate all these things. Okay, see now. Now Vc, as you know, the first part is now Vc. Vc now we have already calculated. Okay, it is 1 lakh newtons. B, breadth B. Baba, breadth B means, but as you know already, the element is the considered element is, okay, it's here now. Considered element is at the junction, but in the web. Baba, how much is the breadth here now in the web? It is 100 mm. So now your B becomes 100 mm. Am I right now? B becomes 100 mm. Okay. So B is known to you. Baba, moment of inertia has been already calculated. Okay, it is there. Then Ay bar. Ay bar is, it is the moment of that area. Okay, sir. Now moment of that area up to the CGC. Okay, area of the web is 200 mm into 100 mm. Okay, so now I will show you again the figure. Okay, see now. This area is 200 mm into 100 mm is the area. It is this area I have considered. In a sense, below the point element, I have to consider the area. This area. Either you can consider this area or above. Above means it is so much. Below means it is so much. So now, since below I have got only one area, it becomes easy for me to calculate. So I am considering this area. So area is 200 mm into 100 mm into lever arm. Lever arm is from here to CGC. Baba, full thing is 250. 250 minus 50. Okay? 350 minus 50. 300 mm is the lever arm from here to here. Okay? So now Ay bar is calculated. Okay? See now. The same thing I have written. Ay bar is 200 mm into 100 mm is the area. Lever arm is 350 minus 50. So it will give me Ay bar as this much. Baba, fill in this equation. Tau v is equal to Vc Ay bar divided by Ib. Everything I know. Okay, just now all the values are here. So your tau v value is 1.47 Newton per mm square. In a sense, at that point or on that element, the tau v value is 1.47 Newton per m square. Okay. See now, also in this problem, since he has not stated anything about the vertical pre-stressing, okay, I can take sigma y is equal to 0. Am I right now? Tau v we have calculated. Sigma y is 0 because he has not said anything about vertical pre-stressing. So since vertical pre-stressing is absent, I am taking sigma y is equal to 0. Okay. So now with this, now the principal tensile stress is given by either it is sigma minimum or I will call it as FCT. Okay, is given by, as you know, this is the equation, sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 whole square plus tau v square under root. Okay, here now sigma x is there, sigma y is there. Sigma y, just now we came to know that it is 0. Tau v, just now we have calculated. And now what about sigma x? If I know sigma x, I think the entire sigma minimum can be calculated. Baba, sigma x can be calculated by this thing now. See now, sigma x means it is the stress in concrete because of the pre-stress application. Baba, the stress diagram he has given 12 Newton per m square on the top, and it comes down to 1 Newton per m square here. Baba, my element is now here. On this element, what is sigma x? This is sigma x. This value is sigma x. You have to calculate this. Okay. So now, Baba, from here to here, it is 1 plus this much. Am I right now? 1 plus this much will give me sigma x. Baba, this much can be calculated by the similar triangles. I have got one big triangle here. Am I right? And another small triangle here. These two are the similar triangles, and I think you can easily calculate the value of this. 1 plus this will give me sigma x. Am I right now? So I think you can easily do that. Okay, sir, now? So now if you do that, you will get sigma x is equal to so much. Sigma x is equal to, okay, 1 plus 12 minus 1 divided by 600 into 100 will give me 2.83. So now sigma x is also known to me. Baba, fill in this equation. All the things are known to you. So either you can calculate FCT or sigma minimum. Okay. So your sigma minimum or FCT is now 0.63 Newton per mm square. Baba, I have put here minus sign because it is sigma minimum. It is principal tensile stress. Tensile stress always carries minus sign. Okay, so principal tensile stress is minus 0.63 Newton per mm square. Okay, this one thing. So now the next point is now, Baba, now I think I can easily calculate the allowable tensile stress. Baba, allowable tensile stress, again it is in the note. Baba, FT is given by 0.24 times under root of FCK. Okay, so 0.24, we have used M40 grade of concrete. So your allowable tensile stress is now 1.52 Newton per m square. Baba, your existing principal tensile stress is 0.63. But allowable tensile stress is how much now? 1.52. Am I right? Your tensile stress is much less as compared to your permissible tensile stress. So I say that the section is safe in shear. Am I right now? This is how it can be done. But now, again, Baba, the problem is not yet over. Baba, now, again, your IS code says that you will have to consider one element at the CGC. Okay, at CGC, I have to now consider. Baba, now for this element, again, I have to calculate tau c, etc., etc. Okay, see now. So now, second one, consider the element at the CGC. Baba, now VC remains same, B remains same, B is in the web only, I remains same, am I right? AY bar, Baba, AY bar means I have got two areas now here now, okay? Two areas are here, please see here now, AY bar, this is one area, okay? I think you can 150 mm by 100 mm, and it's a lever arm from here to here, okay? You can easily calculate, plus this is the area 400 mm by 100 mm, and the lever arm is now from the CG to here. Okay, I think you can easily calculate it. So now that also you can easily calculate it. A y bar works out to be so much. So now tau v can be now easily calculated. It is the Vc ay bar divided by Ib. Vc you know, ay bar just now you have calculated. I you know, breadth is 100 mm. So your tau v works out to be 2.24. Okay, and as you know, since vertical precessing is absent, okay, sigma y is 0, and again sigma x can be calculated by the similar triangles of the stress diagram. Okay, sigma x can be calculated. So now you can easily calculate the principal tensile stress FCT or sigma minimum by the same equation. Okay, fill the value and you can easily find the value of principal tensile stress. And now you know that this is also less than your permissible tensile stress. Okay, less. So I say that totally the section is safe under shear. Okay, thank you very much.